Okay, you will learn about the ARC-Mega32 program control instruction. So let's look at the program control instruction. Okay, so the program control instruction used to direct the flow of the program and allow the flow to the program to change. Okay, so you have two types of program here. Okay, one is from top to bottom. Okay, which is this is a sequence programming. Okay, and then the second one here. Okay, you have the some sort of program control, which is from top. Okay, and then you go to the bottom, and then suddenly you go back to your top, and maybe sometime you go here and there. Okay, so you have two type of program here. One is a sequence programming, and the other one by using the flow control. Okay, the program control. Okay, so the most basic kind of program control is by using the skip and compare and branch or jump. Okay, there are two types of program control here. One is a conditional program control, and the other one is an unconditional program control. Okay, so this conditional and unconditional depending for the unconditional program control. So means that you force your program, okay, to jump or to branch without any condition met. Okay, but for the conditional program control, what you're going to do is the program will be branches, or the program will be jumped to the location, okay, to the specific location if a certain condition is met. Okay, so this is the most basic kind of program controls, which is we can use the skip and compare. Okay, in which here indication of a short change relative to the current program counter means that if you use the skip and compare, so this is a short distance branches. Okay, while if you use the branch or jump, so this is an indication of a change in program counter that is not directly related to the current program counter. Means that this is a long distance branches. Okay, so you have two type of program control. One is a short distance, and the second one is a long distance. Okay, short distance you can use the skip and compare. One long distance you can use branch or jump. Okay, so let's look at the compare and skip instruction. Okay, the one that has a shortest distance. Okay, so there are few instructions for the compare and the skip instruction. One of them is a SBRC. So SBRC stand for skip if bit in a register is clear. So you will skip the instruction just below the this instruction SBRC if the register, okay, a specific bit in the register is clear. Okay, so SBRC instruction test a single bit in a register and skip the next instruction if the bit is clear. Okay, so for examples here, okay, so before that, okay, so this is the syntax of SBRC, RB, and B. So RR and B. So RR is your destination register, which is from R0 to R31, and B is 0 to 7. Okay, this indicate the bit location. Either it's a bit 0 or bit 7, and this is the operation. If RB, okay, bit in if the bit in your register is equal to 0, then what happened here? You skip the next instruction and do the following instruction. Okay, for examples here. Okay, let's look at this one here. Okay, sub R0 R1. Okay, means that you're going to subtract R1 minus R0 and put the result in R0, and then you check whether the output produced from this subtraction, okay, is clear or not at bit 7, okay, by using the SBRC R07. Okay, if bit 7 inside R0, okay, this is R0. Okay, after you perform the subtraction here, okay, then the result would be 100100011, for example. Okay, so this is the result after the subtraction. So then you did this SBRC R07. So what happened here is, okay, so the CPU will check bit 7, okay, in R0, okay, and test it whether it is clear or not. If it is 1, so what happened? You need to do the next instruction, which is you need to execute sub R0 R1. If this bit here is 0, means that the bit 7 is clear. So what happened is you just skip this SUB R0 R1 and then go to NOP. Okay, so when you perform this instruction here, when you execute the SBRC, you see here none of the flags are affected. Okay, so this is what the SBRC do. Okay, you check a certain bit inside of the register whether it's clear or not. If it is clear, then you skip the next bit, the next instruction, and do the following do the other instruction below here. And if it is 1, then you need to do the next instruction. Okay, then we have the SBRS. So SBRS stands for skip if bit in register is set. Okay, so please correct this one here. So this becomes SBRS. So this SBRS instruction tests a single bit in register and skip the next instruction if the bit is set. So now this instruction are going to check whether your bit is set or not. If yes, then you skip the next instruction. If not, then you need to execute the next instruction. So this is the syntax SBRS RRB, which is your RR can be from 0 to 31, while B is the location of your bits. Okay, so if the bit in the if the bit in your RR, your register, equal to 1, so what happened here is you skip the next instruction. Okay, for example here, again, we have this example. Sub R0 R1 means that you're going to subtract R1 from R0 and put the result to R0. And then you have the SBRS R07. Okay, let's do your R0 now. After the subtraction, you have this number here. Okay, so what happened here? Now we are going to check bit 7. Okay, so since bit 7 is 1, so what happened? You skip NAD R0 and do NOP. Okay, so you just skip this instruction here. If R0 is equal to 0, okay, if R0 at bit 7 is equal to 0, so what happened here is, okay, you need to do the NAG R0 and then after that execute NOP. Okay, means that you cannot skip the next instruction after the SBRS. Okay, so again, there is none of the flags are affected by using the SBRS instruction. Okay, next we have the CP. Okay, the CP stand for compare. Okay, so this instruction perform a compare between two registers. Okay, so you're going to compare your destination register and your source register, and none of the register are changed. Mean that after you do the comparison, okay, the value of your RR and RD unchanged. Okay, so all condition branch can be used after this instruction. Okay, why are we going to use this CP instruction here? Because we're going to check the status register. Okay, the flag inside of the status register. You see here, the flag of inside of the status register, okay, will update it according to this operation. Okay, so this is the syntax CPRDRR, in which the operation here is RD minus RR, and then after you execute this instruction, the flag down here will be updated. Okay, so for example, CPR4 R19. So you're going to compare value inside R19 and value inside R4. Okay, then you following by the branch instruction here. Okay, BRNE not Q. Not EQ means that this is a label. Okay, if R4 not equal to R19, so what happened here? It will branch to this location. Okay, so if R4 not equal to R19, so this is what this instruction do lah. Okay, if R4 not equal to R19, then you need to jump to this and on not Q destination. If R4 is equal to R19, so what happen? So you will do the following instruction. Okay, the next instruction after the BRNE instruction. Okay, so this is the flags that are affected every time you do the CP. Okay, H flag, S flag, V, negative, 0, and carry flags. Okay, then we have the CPC. Okay, so this CPC stands for compare with carry. So this CPC instruction perform a compare between two registers, RD and RR, and also takes into account the previous carry. So again, okay, none of these register RD and RR are changed. Okay, so the range after you did the CPC, RD and RR value unchanged. Okay, so all the condition branches can be used after this instruction. Okay, so this is your operation RD minus RR minus IC. So what happens after you execute this instruction? The flag inside of your status register will update accordingly. Okay, so this is the syntax CPC, RD, and RR. Okay, let's look at these examples here. Okay, so now you're going to compare, okay, 16-bit number. Okay, you have a 16-bit number which is consists of R0, R2, and R3. So you have a 16-bit number. Okay, you're going to compare whether this 16-bit number is equal or not. Okay, so the first number is stored inside of R2, R3, and the second number is stored inside R1 and R0. So in order to do that, okay, first you compare the, okay, since this is a 16-bit, okay, you can divide it into 2 byte here. One is a low byte and one is a high byte. Okay, first, what you're going to do is here is you compare the lower byte. After that, you compare the high byte. Okay, and then follow by the branch instruction. Okay, there are a lot of branch instruction. One of them is a BRNE, means that this one here, the BRNE is actually stand for branch not equal. Okay, if the R3, R2 not equal R1, R0, so what happen? You will branch to this destination location. If R3 and R2 equal to R1 and R0, so what happened here? Okay, you need to do the next instruction after the BRNE. Okay, so this is what happened. Okay, by using the CPC. Okay, then we have the compare with immediate. Okay, So this is similar to what the CP and CPC. Okay, so but this one here, okay, instead of you compare between two registers, now you compare with an immediate value. Okay, so the CPI instruction perform a compare between a register RD and a constant, okay, an immediate value. Okay, and none of the register your RD are changed. Okay, means that your RD not change. Okay, remains. The value of RD is remain. So all condition branches can be used after this instruction. So this is the syntax CPI RD with K. Okay, again, since this one here involve the immediate value, so your operand of RD, okay, your register must from R16 to R31. Okay, while your K is your value from 0 to 255 lah. Okay, and this is the operation which is RD minus K. After this operation is executed, so what happens? The flags inside of your status register will be updated accordingly. Okay, for examples here. Okay, you are going to compare the value of R19 with 3. Okay, if the R19 equal to 3, what happened? Okay, because this one here we use the BRNE. Okay, we use the BRNE. If R90 is not equal to 3, what happens? You're going to branch to this destination. If R19 is equal to 3, so what happens? You need to do the next instruction after the BRNE instruction. So this is another what we call here, another instruction, okay, which is you need to do a comparison before you do the branches. Okay, then we have the CPSE. Okay, the CPSE stand for compare, skip, if equal. Okay, so this one here, no need to after you use this instruction, no need to add a branch instruction after that. Okay, so the CPSE instruction perform a compare between two registers, which is RD and RR, and skip the next instruction if RD equal to RR. Okay, so this is the syntax CPSE RD RR, which is this is the operand. Okay, RD and RR can be from R0 to R31, and this is the operation. If RD equal to RR, what happens? You jump to that to the destination, okay, to the label destination. Okay, for examples here, INC R4, okay, so you increment your R4, and then CPSE R4 with R0. Okay, if R4 equal to R0, so what happens? You skip the NEG instruction and do the NOP. If R4 not equal to R0, so what happened here? Okay, you're going to do the NEG and then following by the NOP after that. Okay, so that is the CPSE. Okay, for the CPSE, none of the flags are affected. Okay, any question up until here? Okay, so this is the short distance branches. Okay, we have learned about a few instructions here. Okay, you have the CPSE, and then you have the SBRS, SBRC, and then if you're going to do a branch, okay, which is you're going to branch to a longer distance, then you need to use the compare instruction. Any question up until here? Ada soalan tak?
Yes, Doctor. I've noticed some of the instructions have less than one CPU cycle. Like, for example, this one, it has 2/3 if it's true. How does that affect the total like cycles or the the operation of the CPU?
Okay, this one here. Okay, for example, this one here. Okay, if the instruction is false, so what happened here? the CPU cycle is 1 CPU cycle. And what if the instruction is true, or if the condition is true, then what happen here? The CPU cycle will take 2 to 3 cycles, not 2 over 3, 2 to 3 cycles.
Oh, this is not 2/3.
Not 2 over 3. This is 2 to 3. Either 2 cycle or 3 cycle. Okay, depending on the next instruction. Okay, sometimes the next instruction it will have 2 cycle. If this instruction here is quite bigger, and then it will become 3 cycles of instruction of CPU cycles. Not 2 over 3. Yeah, this is a 2 to 3 cycles.
Okay, doctor. Thank you.
Okay, then we go to the jump and branches. Okay, so the jump or branch instruction have 2 types. Okay, so one we call it as an unconditional branch or jump, and then the second one here we call it as a condition branch or jump. Okay, for the unconditional branch, okay, means that when CPU execute an unconditional jump, it jump unconditionally without checking any condition to the target location. Okay, means that okay, you force your CPU or your program counter to jump to the location without need to check any condition. Okay, so the example of unconditional branch is such as RJMP and JMP instruction. While for the conditional branch, okay, when the CPU execute a condition jump, so it checks a condition, means that it will check your status register, okay, your flag inside of your status register. Okay, depending on that, on this flag here, if the condition is true, then what happens? It will jump to the target location. Okay, otherwise, it will execute the next instruction. Okay, so this is the difference between the unconditional branch and conditional branch. Okay, one without checking the condition, okay, without checking your flag inside of your status register, and this one here, you're going to check the condition, which is the flag inside of the status register. If the condition is true, then you jump to the target location. If not, then you need to execute the next instruction. Okay, so let's look at the unconditional branch. Okay, there are 3 unconditional jump or branch in AVR. Okay, one of them is JMP instruction. So this JMP instruction is used to jump to an address within the entire program memory. Okay, depending on the memory size lah. If the memory size is bigger, then it will go to the entire program memory. Okay, while for the RJump, okay, jump to the address within the PC2K plus 1 and PC2K plus 1. But this one here, quite similar. The RJump and jump is quite similar. Okay, it is also can jump to address within the entire program memory. Only the way it calculates the location are different. Okay, the way it calculates the destination location is different from JMP and RJMP. While IJMP, so I just call it as an IJump. Okay, so this one here jump to the address pointed to by the pointer register Z. So for the IJump, you're going to see what are the address that are pointed by your pointer register Z. Okay, so the location where we want to jump is labeled, okay, by using a unique name followed by this column here. Okay, so this is the label. Okay, and this is your label. Okay, so means that when you do RJump L1, means that you're going to jump to this location here. Okay, to L1 location. Where is your L1 location? We see at this location. Okay, so then in front of the jump instruction, we mention the name of the label. Okay, so this causes the CPU to jump to the location we have labeled instead of executing the next instruction. for example, this one here, so this is an unconditional branch. Okay, so first we execute line by line. Okay, we execute the first instruction, second instruction, and the third instruction. Suddenly, then you have a RJMP L1, means that you need to go to this L1 location. Okay, this target location. And then you do the again ADD R16, R17, and then after that you have RJMP L1. So you go again to this L1 location and do this thing. Okay, so I just want to ask you, is it the what we call here the last instruction here? Okay, it's execute or not? Can you tell me this last instruction SBRC R50, is it this instruction is execute or not execute at all?
No.
Okay, so this
It's not
instruction, okay, this SBRC R15 will never executed. Okay, why? Because you always force your, okay, you always forced to jump to this location. So this SBRC R15 will never execute.
But Victor, I think there is no condition to this infinite loop.
Yes, there is an infinite loop. Because why? Because this is an unconditional branch.
Yeah.
Okay, so that's why it's an infinite loop inside of this two instruction here. Okay, it will keep looping until you stop the program. Okay, so let's look at the more detail on the unconditional branch instruction. Okay, we have the JMP. So JMP stands for a jump. Okay, so this instruction jump to an address within the entire program memory. So this is the syntax JMPK. Okay, by right, this K here is referred to your program memory address. But to simplify it, okay, we can change this K to a label. Okay, just use a label that you can use the JMP. No need to know the program memory address. Okay, so what happened to, so this is the operation. Okay, you can see here PC. Okay, K go to your PC means that this K value here, okay, the program address will be load to your program counter, and then the program counter will ask the CPU to go to that location. Okay, so for example here, we have the MOV R1 R0. So this is the first instruction, and then suddenly JMP for PLC. Okay, so this is an unconditional jump. So what happened? You will jump to here. Okay, what about the instruction below here, below the JMT? Is it executed or not? Not executed. Why? Because you already asked this instruction to go to this location. So whatever instruction below the JMP will never be executed. Okay, so this is in JMP, the operand contains the address of the destination. Okay, when JMP is executed, PC is loaded with the operand value. Okay, so I just going to show you the difference between JMP instruction and RJMP instruction. Okay, so let's look at this instruction here. So this is your program. Okay, you have a program, and this is your program memory. Okay, which is it. Okay, you started your program memory at 0. So that's why the first instruction here is stored at 0, 0, 0, 0. The second one here is 0, 0, 1 until the last one here is 0, 0, 7. Okay, and then you have all the instruction you store inside of this program memory. And then the yellow line here, this is your program counter. Okay, recall back the fetch and execute cycle, okay, which is involved the program counter. The program counter always one step ahead of the execution instruction. Okay, so let's look at here. When your PC point to 0, 0, 0. Okay, so what happened? Now you're going to fetch this instruction LDI R16 15. Okay, and then the program counter point to the next instruction, and then what happened here? You currently execute the first instruction, which is LDI R16 15, and then the program counter increase. Okay, which is now you see here the program counter pointed to 002, which is it going to fetch this instruction here, but at the same time it's just executed this instruction LDI R17 5. Okay, and then here you see the JMP label name, which is the label name. Okay, you're going to see you're going to jump to this location. Okay, since this label name here is at address 006, so that's why 006 is placed to your program counter. Okay, so now what happened here? Okay, the CPU know that, oh, now we are going to jump to this location, which is at 006. So if we go to this location, do the ADD R16 R17, and then it execute the JMP label name. So once more, you see the label name. The label name, what is the location of the label name? Is at 006. So it will jump, load the 006 location to your program counter, and then CPU will go to this address again, and it will keep repeating. Okay, so this is what happens when you use the JMP instruction. Okay, next we are going to see the RJMP. Okay, RJMP stands for relative jump. Okay, so this instruction relative jump to an address within the PC-2K plus 1 and PC2K words. Okay, so for AVR, we have a program memory exceeded 4K words, which is 8 kilobyte of program memory. This instruction can address the entire memory from every address location. So this is the syntax RJMP, which is K is actually your program memory address, and then this is the operation, which is you see here. Okay, the way it's calculate the target location is different compared to JMP. Okay, in which your JMP, for the JMP, you just simply put the what we call here, simply put the program memory address to your program counter. But this one here, okay, you're going to add your PC plus with your program memory address. Okay, the difference between your program memory address and plus with 1. Okay, the way it takes the calculates the target location are different from JMP with the RJMP, but it do the same thing, which is you're going to jump to the target location. Okay, for examples here, okay, let's look at this example. Okay, you have the CPI R1642. So what happened here? You're going to load this value to R16 and then BRNE. Okay, no, sorry. CPI R1642, you're going to compare R16 with 42. Okay, if the R16 equal to 42, what happened? Okay, you will do the next instruction. If R16 not equal to 42, so then after that, you go to this error. Okay, and then, okay, let's say like this one here, R16 is equal 42. So what happened? You go to this RJump OK, and then you see RJump OK, and the target location is OK. So you jump to this location. Okay, so this is what happened when you use the RJump, which is a relative jump. Okay, so let's look at this example here. So how the relative jump works. Okay, so you have the same program. Okay, now we just simply replace the JMP with the RJMP. Okay, so this is the same program. Okay, similar to the one we did earlier. Okay, so this one, and then okay, you see this is your program counter. Okay, your program counter will keep increasing until here. Okay, so you see the RJMP L. Okay, now you're going to execute this line. So what happened here is, okay, so 002 plus with 003, and then now you're going to 005. Okay, previously what happened? When you what we call here, when you use the JMP, we just simply take the location, the program memory address for the label name, which is 005, and load it to your program counter. But now what happened here is you need to add 0002, which is the current program counter, plus with how many program memory that you need to go in order to go to this target location. In this case here, in order to go to 005, you need to add with 003. Okay, and then now you see here RJMP label name. Okay, now you're going to go to this location. So what happened? You need to add 006 with FE. Okay, so this is, then it will come back to your 005. Okay, just the way it put the program counter is quite different compared to JMP. JMP, you just take the address of the target location, but this one here you need to calculate what are the difference between your program counter to the one that you're going to jump. Okay, then let's look at the IJMP. So IJMP stands for indirect jumps. So this IJMP instruction indirect jump to the address pointed by the pointer register Z. Okay, so the Z pointer register is a 60-bit one and allow jump within the lowest 64 kilohertz section of the program memory. So this is the syntax. You just use the IJMP, and then suddenly the program counter will jump to the target location that are pointed by your program counter, as by your your pointer register Z. Okay, so for example here, okay, MOV R31 R30. So what happened? IJump means that now you're going to lompat, okay, to jump, to branch to the location that are pointed by R31 R30. So let's say like if R31 and R30 is pointed to this location, okay, then what happened? It will jump to address 0100. I can and do the execute that instruction. Okay, so any question for the unconditional branch? Okay, we have finished the unconditional branch. Okay, you have a 3 type of unconditional branch. Okay, one is a jump, JMP, and then you have a RJump, and the last one here is IJump. Okay, JMP and RJump is quite similar. Okay, only the way the PC get the address is different. While IJump, okay, this one here you will jump to the target location that are pointed by pointer register Z. Any question up until here? Ada soalan tak?
So I want to ask, is there any condition we can use only for our jump instead of jump, or is there any condition we can use jump instead of our jump?
Okay, usually there is no condition which one you're going to use, but usually, okay, most of the programmer will use the JMP instead of the RJMP. Okay, it depends on the programmer itself. There is no rule of thumb which one you're going to choose.
Okay, yes, sir.
Okay. Okay, so now let's look at the conditional branch. Okay, while it is useful to be able to jump around in your code using the JMP, IJMP, RJMP, they certainly don't solve all the problems. Okay, so in order to write any real program, okay, you need to be able to branch conditionally based on the current state of the program. Okay, the good way to do the branches is by checking a certain condition, not force the program to jump unconditionally. Okay, so the condition are stored inside of your status register, which is this condition actually refer to your flag, okay, inside of your status register. So the conditional branch instruction examine bits in the status register and choose between two course of action. Okay, so this status register bit are either updated after a certain instruction have been executed or explicitly updated. Okay, so the first one here, updated after a certain instruction have been executed. This one here, okay, you can see every time you do the data processing, which is arithmetic unit, logical operation, some of the flags inside of the status register will be updated accordingly. Okay, so this is the first one. Okay, how the condition, how you're going to check the condition, or you can explicitly update it by using the test and compare instruction. Okay, previously we already learned about the CPI, CP, and CPC. Okay, so to check the status register, you can use this instruction and the status register will be updated explicitly. Right? So let's recall back the status register. Okay, so this is your status register. Okay, it consists of 8 bits. Okay, in which you have the carry flags, zero flag, negative flag, overflow, sign, half carry, test flag, and interrupt flags. Okay, so most of the time, okay, the flag that we'll be looking at is at this region here, okay, which is at bit 0 to bit h. Okay, so this one here, okay, so let's look at the h flags. Okay, so h flag is a half carry flag. Okay, so this flag is set whenever there is a carry from bit 3 to bit 4, and you have the sign bit. This flag is result of the exclusive OR-ring flags and V flags, while overflow only set whenever the result or the sign number operation is too large, causing the high order bit to overflow into the sign bit. Negative flag, okay, you need to indicate a negative result in arithmetic or logic operation. So this one you need to check at your bit 7, either is a 0 or 1, and then you have a 0 flag, indicate a 0 result in the arithmetic or logic operation. So this one here, you need to check the result. If the result is 0, then Z will become 1. If result is have any values, so the 0 flag will become 0, and the carry flag, this flag is set whenever there is a carry out from the bit 7. So this flag will change according to this description here. Okay, so conditional branch instruction. Okay, so now we're going to familiar with a condition branch instruction. So this condition branch instruction is identified by a mnemonic BRCC. Okay, every time you see the BR, so you know that this is a branch conditional. Okay, CC. Okay, the CC at the back of the BR represent the condition to be checked. Okay, so this is the general form BRCC and followed by your address label. Okay, so if the condition is true, then the control will branch to your address label. Okay, so no effect on the conditional codes. Okay, so this is the what we call here example of the conditional branch instruction. Okay, you have a lot of conditional branch instruction here. Okay, you have the BREQ. BREQ stand for branch if equal. So what flags that will be checked in order to see whether is the two register is equal or not? We are going to look at the Z flag. Okay, if the Z is equal to 1, so you know that the two numbers is equal. For example, okay, you have a R0 and R1. Okay, so let's your R0 equal is 10 and R1 also 10. Okay, and then you do the CP. Okay, you compare R0 with R1. So what happens for the CP? The CP do the R0 minus R1. Okay, so the CP operation is actually R0 minus R1, and then check whether, okay, and it will update your flag inside of the status register. Okay, since 10 minus with 10, okay, and then you will get 0. Okay, so what happened here? The Z flag will automatically equal to 1. So if you use the BREQ, means that both R0 and R1 are equal number. Why? Because it's looking at the Z flag. Okay, if you're going to use the BRNE, means that it is only branch if both number are not equal. Okay, which is we're looking at the Z flag as well, which is if the Z equal to 0. Okay, for example, this one here you have D is a 0 and D is a 9. For example, okay, so 10 minus 9, then suddenly you get value. Okay, you get a value X there. So what happened? Z will be updated as a 0. So now you know that these two numbers R0 and R1 are not equal. So that's why we call it as a branch if not equal. Okay, then we have a lot of others conditional branch instructions, such as, okay, the one that we always use, okay, some such as this one here, BRSH, which is branch if the same or higher. Okay, so this one we check the C flags, and BRLO, branch if lower, BRMI, branch if minus. So you're going to check whether the value, okay, the value inside of register is positive number or negative number. Okay, and then we have the BRPL, branch if a plus, means that you're going to check whether it's a positive number, and BRMI to check whether the register is a negative number. BRGE, branch if the greater or equal. BRL3, branch if the less than 0. Okay, so this is the most common instruction for the conditional branch that we always use. Okay, I think we stop here. Okay, in the next class, we go. Tomorrow we will see the details on this instruction here. Okay, any question up until here? Ada soalan tak? Okay, if no question, then we stop here. Thank you, class, and see you tomorrow. Okay, and one more thing.